Yeah, right. Welcome to the second lecture of CO3. So, in the previous lecture, we were trying to calculate the number of free electrons in a silicon, especially at room temperature, and we have identified that we have only one electron for every 5 into 10 power 12 atoms of silicon, if I am not wrong. So this is a very low number if you and we have seen this in the last lecture. So the pure type of silicon is also called as intrinsic semiconductor, and like we have seen from the quantities of number of charge carriers, we can say that it has very high resistance. The number of charge carriers is very low. One electron for every 5 into 10 power 12 atoms per centimeter cube is very low. So how do we increase the number of charge carriers? So that is the challenge that as young engineers we are facing now. So how do we set out to solve the problem? Okay, so it is possible to modify the resistivity of silicon uh, by adding some other materials. Okay, so before going to that, let us uh, see a simple relation. Suppose in an intrinsic semiconductor, that is the pure type of silicon, if the electron density n is equal to ni, we also know that the hole density p is also equal to ni, because a hole is generated only when an electron is generated. So if in an intrinsic semiconductor, if there are ni free electrons, of course there will be ni holes. So what will be the product of electrons and holes? N into p, it of course will be equal to ni square. Okay, so n into p is equal to ni square. This is a kind of an important result. Okay, so you should be able to remember this. So proceeding. Okay, now we come, the aim of this slide is to increase the number of charge carriers, that is electrons. Okay, so here we take a pure silicon, that is nothing but the intrinsic silicon, and we do a process called doping. Okay, so in this particular slide we are doping it with elements which have 5 electrons in their outermost shells. Of course, phosphorus is pentavalent, that is, it has 5 electrons in its valence band. Okay, so when we uh, dope silicon with phosphorus, of course, phosphorus has 5 electrons and silicon has only 4. So this phosphorus atom forms 4 covalent bonds with 4 neighboring silicon atoms, but one of the electrons of the phosphorus atom is left out freely, and it is now available for conduction of electricity. So uh, so this type of controlled addition of impurity is called doping, and phosphorus in this case is called a dopant, and especially it is called an n-type dopant, because adding phosphorus to silicon is giving excess carriers of electrons, and electrons happen to be carrying a negative charge. So that is why uh, phosphorus is called an n-type dopant, and a silicon that is mixed with phosphorus is said to be doped as silicon with phosphorus is said to be uh, doped as n-type. Okay, of course it all makes sense because of the excess electrons that is left out in the pentavalent phosphorus. Okay, um, now we have seen in the earlier slide that the product of electrons and hole densities, that is n into p, was equal to ni square. Now I am curious to know about these densities in a doped material. Now I have a silicon that has been doped with a pentavalent impurity. So even in this case, it is proved that the electron and hole densities n into p, they actually equal ni square. I seriously recommend students to find out an answer for this. Why even in doped materials the electron and hole density is equal to ni square. I seriously recommend students to explore Google and find out an answer for this. Okay, now there is another type of doping. It is doping with p type. Okay, now we have trivalent elements like boron, which has this element has 3 electrons in its outermost shell. So what happens is, with this boron, the boron is able to form uh, 3 covalent bonds, but with this silicon, it is a it is an incomplete covalent bond. It is of course resulting in a hole, which is nothing but a loss of the covalent bond. And now this hole is available for conduction. Okay, so when we dope a semiconductor with the trivalent impurities, in this case boron, and the semiconductor in this case is silicon, so we say that the doping is p type. Because, and of course, as seen here, in when we dope a semiconductor with p type material, the will be majority carriers will be holes, and in n type semiconductors, majority carriers will be electrons in n type, and in p type majority carriers will be holes. Why I say majority carriers here is an n-type dope material also has its own share of holes. Okay, and a p-type doped semiconductor also has its share of electrons. Okay, so that is why these are referred to as majority charge carriers. So majority charge carriers in a p-type semiconductor are holes, and majority charge carriers in an n-type semiconductor are electrons. Okay, so this is the summary. So this is the intrinsic silicon, which has 4 valence electrons, so it can form covalent bonds with 4 other silicon atoms, like you see in this picture. But we know that the resistivity of silicon at room temperature, at the temperatures at which we operate, is very low. So we usually dope the silicon, okay, and we then make it an extrinsic semiconductor. If we take the silicon crystal and we dope it with n-type semiconductor, n-type semiconductors are usually referred to as donors, in this case phosphorus. Okay, so it becomes an n-type semiconductor. Okay, and the majority carriers are holes, like I have discussed previously. And if you take the same silicon crystal, now you dope it with acceptors. Acceptors are nothing but trivalent impurities, and in this case it is boron. So it becomes a p-type semiconductor or an acceptor, and the majority carriers in a p-type semiconductor are holes. Okay, so this should give a nice summary of charge carriers in silicon. Okay, now that where did we start, I would like to give you a brief summary. Now I wanted to explore silicon. Why silicon? Because it is somewhere in between having 8 valence electrons and 1 valence electron, so it has 4 electrons, so I wanted to study its characteristics. But what was wrong with intrinsic silicon is its resistivity is too high. So now what do? I doped it with pentavalent and trivalent impurities, and I made the amount of charge carriers more. Uh, the availability of charge carriers is more with the help of doping, and it has increased. Okay, just increasing the amount of charge carriers is not enough, because I need to able to transport these charge carriers, only then current flows. Okay, so like we all know, I is equal to dq by dt. Okay, so there needs to be some change in concentration or some change in charge with respect to time, only then current actually flows, only then I do get some electrical properties out of the silicon. So transport of charge carriers is a very very important topic. Okay, so there are two phenomenon fundamentally with which transport of charge carriers takes place in semiconductors. Okay, so one is drift. Okay, so the process in which charge particles move because of an electric field, okay, is called drift. Okay, so one of the process with which these charged particles move, okay, is called drift, and drift occurs when there is an electric field. You have to remember the charge carriers move because of drift. Okay, and the drift occurs because of the presence of an electric field. Okay, and of course when these charged particles are in the presence of an electric field, they attain some velocity. Okay, so, and this velocity is proportional, of course proportional to the electric field. Okay, so that velocity v is nothing but mu times e, where e is your electric field, and this mu is called your mobility. Okay, so you need not worry about these formulae, you just get a intuitive understanding of things. Okay, so the velocity in a, so transport of charge carriers takes place with the phenomenon called drift, and drift occurs when there is an electric field, and the velocity of charge carriers attained in the presence of drift is related to the electric field with the help of this formula. So if you are able to understand these three, you are in good hands. Okay, so let me proceed. Okay, and these are the expressions for current flow. I think that is not the object of the course. I don't want to scare you with too many formulae, but understand, I want you to know that there is a solid basis of physics behind it, and whatever conclusions I seem to make are not just out of thin air, but they have solid base of physics behind it. uh, okay, so I just don't want to scare you guys, but I just want you to remember that current flow or the charge carriers, transport of charge carriers takes place in semiconductors with the help of drift, and drift occurs when there is an electric field. Okay, so I want you to understand these three. Transport uh, happens with the help of drift, and drift occurs in the presence of an electric uh, field, and that velocity attained by the charge carriers in the presence of electric field is related as v is equal to mu e, where mu is nothing but mobility. So these three things I want you to remember, and of course there is a solid base of physics. I just want you guys to be aware of things that are going on, but I don't want you guys to read too much into these things, because this is not the objective of the course. Okay, right. So there is another phenomenon apart from drift, with which charge transportation actually takes place, which is nothing but diffusion. Okay, so what is diffusion? So you take a glass of water. Okay, suppose this is a glass of water. Now you add an ink drop to it. You add an ink drop it. What happens is nothing but diffusion. This ink drop soon changes the color of the water, and it becomes completely diffused into the water. See, the same thing happens over here also. So charge particles move from region of high concentration to a region of low concentration. Suppose this is a p-type semiconductor which has majority of holes. Okay, and suppose I inject electrons at this interface. I inject electrons. So what is happening at this interface is this electron sees a very heavy concentration gradient. Okay, so there are very less uh, uh, electrons many number of, or rather many number of holes this side, so there is a high concentration gradient in this region, in this p-type region. So what happens is this electron becomes your ink drop, whereas the p-type material that is present over here, or the holes that are present in the p-type material, those become your water molecules, and diffusion takes place, just like the phenomenon that I described here. So the electron becomes your ink droplet, and the holes of this p-type material become the water molecules, and then diffusion immediately takes place. Okay, so basically you need to understand that there are two phenomena with which transport of charge carriers is taking place. The first one happens to be drift, which of course happens in the presence of an electric field, and the second one happens to be diffusion, which happens when there is a concentration gradient. Okay, so very important. These 2 points are very, very important to get a intuitive understanding of semiconductors. Okay, so there are two phenomena with which charges are carried in semiconductors. Okay, the first one is drift, and drift happens in the presence of an electric field. The second one is diffusion, and diffusion happens when there is a concentration gradient. Okay, so let me move ahead. And of course, like I said in the previous slides, don't be too much worried about all the formulae. You did not remember this, because this is to let you know that there is a strong base of physics. I am not making out things out of thin air. Okay, but one thing you have to understand is mm, the current in drift is proportional to the mobility factor, whereas the current, I'll make it I drift, I diffusion is proportional to a constant called d. Okay, it is called the diffusion constant. Okay, the constant that pops up in drift is called mobility, and the constant that pops up in the diffusion equation is called diffusion constant. Okay, so you need to understand these two. Okay, and there is a beautiful relation that actually relates the diffusion constant and the mobility. So d by mu is actually called kt by q. Here k is your Boltzmann constant, so k is your Boltzmann's constant. Of course, T is your temperature in degree K, and Q is the charge of electron. So this beautiful relation is named after Einstein, and it is called Einstein's relation. Okay, so again, like I said, there is a proper underlying physics behind it, but that is not the objective of the course, so I am skipping it. Okay, now that we understand uh, what a p-type semiconductor is, what an n-type semiconductor is, now I would like to understand what a p-n junction is. Okay, so now I put a p-type semiconductor, so this bar is doped with trivalent impurities. Okay, and this is an n-type semiconductor, so this bar of semiconductor is doped with pentavalent impurities. Now I put these two side by side. Okay, so this is nothing but, when you put these two together, it is called a p-n junction diode, and this is the symbol of the p-n junction diode. So the n-type region corresponds to the vertical bar. Okay, so which is also called as the cathode, and the p-type region corresponds to the base of this triangle, which is also called as anode. Okay, so it is very important. Okay, so this is how you draw the symbol of a diode. Okay, so the vertical bar is nothing but the n-type, which is also called as cathode, and the base of the triangle is the p side terminal, and it is also called as an anode. So it's very important. Going forward, we'll be using these two terms, p and n, anode and cathode. Okay, so it is important that you remember this. Okay, so diode, basically the PN junction diode has three regions of operation. Okay, very important to understand these three. Okay, so the first region of operation is when PN junction is in equilibrium. Okay, the second region of operation is when the PN junction is under reverse bias, and the third region of operation is when the PN junction is under forward bias. Okay, so we'll see each of these regions for better understanding of the diode. Okay, so like I discussed, in the p-type semiconductor, the majority carriers are holes and they are referred to as p subscript p. So here this p stands for the charge carriers, and this p for the p-type semiconductor. So in the same p-type semiconductor, we also have electrons of minority carriers. Similarly, on the n side, we have electrons as majority carriers and holes as minority carriers. Okay, now if I put p and n regions together, so now what happens at the junction? So this is called the junction. Okay, this or the interface between p and n. Okay, so what happens is the electrons from the n-type region see a concentration gradient of holes and vice versa, and the holes in the p-type region see a huge sea of electrons over here, and the electrons in this n-type region see a huge sea of holes over here. So what happens is uh, both the electrons and holes from p-type and n-type see a large concentration gradient. And what did we conclude in the previous slides? When there is concentration gradient, which phenomenon comes into picture? Yeah, the diffusion comes into picture. And what happens is lot of electrons from this n side diffuse into the p side, and similarly holes in this p side diffuse onto the n side. So a lot of activity is going on at this interface. Okay, so this is at time t is equal to 0. I have introduced the n type and p type together. Okay, like you see, these pluses are nothing but the sea of holes on the p type semiconductor. These minuses are nothing but the huge amount of electrons that are present in the n-type semiconductor. So when I introduce that this is the picture that occurs at t is equal to 0. So after some time t is equal to t1 time units, what is happening? Okay, so the junction or sorry for that. So the junction over here uh, is actually witnessing lot of activity. Holes from this side moving to this side, electrons from the n side moving to the p side. Okay, so once the electrons move to this side, what actually happens? Because there are many number of holes over here, electron hole recombination takes place at the immediate vicinity of this interface. Okay, similarly holes that are coming from the p side see a huge number of electrons on the n side. Again, electron hole recombination happens. But as you can see, uh, at the interface on the n side, you can see positive donor ions that are developing at the interface, and on the p type you can see negative acceptor ions uh, that are developing. Okay, so why these are formed is because the holes from this side are diffused like madly. They are getting diffused into the n-type region, and they are madly recombining after moving into the n-type region. Similarly, the electrons in the n-type region are madly getting diffused into the p-type region, and once they diffuse into the p-type region, they are combining with the holes that are present over here. Okay, so what is happening near the interface is an interesting phenomenon actually, because of the mad activities of electron hole interaction that is taking place from either side. Electrons from this side moving to this side and recombining, and holes from this side diffusing madly to this side and recombining. What actually happens is, the atoms that lose the electrons, they now become ions. Okay, these are positive ions because these don't have the electrons anymore. Similarly, on the p side, these are negative ions because these don't have holes anymore. Okay, and mind you, at the interface again, if there is any free electron or free hole, they are busy recombining with the available electrons because there is an ocean of electrons here. And the atoms that are devoid of any electron, they become positively charged donor ions. Okay, and the donor ions have been appropriately, what do you say, encircled, so that in order to indicate that these are not ready for any kind of what do you say, reaction. The reaction is already taking place only between electrons and holes. But what is happening slowly and gradually at the interface is, on the n type, positive donor atoms are being piled up, and on the p type near to the interface, negative acceptor ions are being piled up. So after considerable amount of time, say at t is equal to infinity, what is happening is, the region, or what do I say, near the vicinity of this PN junction, the vicinity is filled up with donor ions and acceptor ions, and these donor ions and acceptor ions are actually immobile. They are very tough, and they not very tough, they are immobile, and they don't actually move. Okay, their mobility is very low. Okay, so this region of fixed ions is known as depletion region. Okay, so this region in the vicinity of the interface, okay, which is now filled up with ions, is called depletion region. Now a beautiful phenomenon takes place. Okay, please follow. Okay, so now sorry for that. Uh, what happens is, because these are positive ions on the n side and these are negative ions on the p side. Okay, we know that an electric field exists from the positive direction to negative direction. So see, that is what is happening here. An electric field E is now developed from this positive ions to the negative ions. Okay, see, when I say an electric field, what should come to your mind immediately? Okay, so what we learned about transport of charge carriers. Transport of charge carriers takes place through two phenomena. The first one is drift in the presence of an electric field. The second one is diffusion in the presence of concentration gradient. Now what is happening because of this electric field? See, a beautiful phenomenon. Because of this electric field now results in a drift, and this drift results in a current. Okay, so what happened at t is equal to 0? A seemingly harmless p and n. Okay, so what happened? Because of the concentration gradients, there has been a current flow, and because uh, of that rapid movement of holes and electrons from either side, what happened near the interface is positive donor ions forming on the n side and negative acceptor ions forming on the p type. So because these are positive and negative charge, this results in an electric field from positive to negative direction. So what happens at this equilibrium condition is, the current that results due to this electric field, it actually opposes the current that is due to the diffusion. Okay, beautiful, isn't it? So what happens at equilibrium is, the drift current that is flowing from N to P, it cancels out the diffusion current that is coming in the opposite direction, and it exactly cancels. So the net current flow across the junction is equal to 0. Beautiful, isn't it? So when do you say the PN junction is in equilibrium? When the net current flow is equal to 0. So how is this net current flow equal to 0? The net current flow is equal to 0 because these two physical phenomenon, are cancelling out each other. Okay, this is a beautiful phenomenon, and it usually takes place only in semiconductors. Okay, so basically the drift currents equal the diffusion currents, and they are equal and opposite, and they cancel out. So when a PN junction is in equilibrium, the amount of current that is flowing is equal to 0. Okay, right, again there are some equations, again you shouldn't bother yourself. I just put these equations in the slide so as to make you aware that there is solid physics behind that is going behind it. Okay, right, now we'll go to the second condition, which is diode in reverse bias. Okay, so when do we say the diode is in reverse bias? This is the condition. So when the n-type region is connected to a higher potential than the p-type region, the diode is said to be under reverse bias. See what is happening here. The n-type is connected to a positive potential. A positive potential is of course higher than negative potential, and this negative is connected to p. So here n-type terminal is at a higher potential compared to p. So this is what do you say, in reverse bias. Now again, what is happening in this reverse bias? So we know that potential and electric field already go hand in hand, isn't it? Okay, so this potential now will result in its own electric field. Okay, and where does the electric field go from? Remember, electric field is a vector, and it goes from positive to negative. Okay, and what is the built-in electric field in the equilibrium? In which direction is it in the previous slide? If you remember, the built-in electric field was also going from positive to negative. Now because of this reverse bias, the applied external electric voltage is aiding the built-in electric field, isn't it? Whatever is the built-in electric field, okay, that is being further aided by the external electric field that is occurring due to the presence of the reverse bias voltage. So in effect, what happens is the external voltage strengthens the built-in electric field, and the depletion region width, as you can see in the slide, the depletion region width actually increases. So if this is the depletion region width in equilibrium, when you reverse bias it, what do you see? The external voltage is aiding, or it is strengthening the built-in electric field, that is resulting in an even more wider depletion region. Okay, so what happens in reverse bias is the depletion region is even more wider. Okay, and very important conclusion I am drawing here: the junction in reverse bias, the junction carries negligible current. Okay, the reverse bias, the depletion region is too high. If it is PN under reverse bias, the depletion region is too high. Okay, now no electrons can from the n side move to the p side, and vice versa. No holes from the p side are now able to move to the n side. Okay, so there is negligible current under reverse bias because of this increased width of depletion region. Okay, right, so this is one of the applications of diode in reverse bias. So as I increase this reverse bias voltage, what happens is the width of this depletion region increases, and this depletion region and N and P type can be modeled as a capacitor. Okay, so this N type forms one plate, p-type forms another plate, and this depletion region forms the dielectric. Okay, now what happens when I increase the reverse voltage? When I increase the reverse voltage, of course the depletion region width increases, and when the distance between the two parallel plates increases, so we know that C is equal to epsilon A by D, and when the distance increases, of course capacitance decreases. Okay, so this is what happens. This is one of the applications of diodes in reverse bias. Of course, we have concluded in previous slide that the reverse bias current is actually zero, but one of the very good applications of diodes in reverse bias is it can be viewed as a capacitor. Okay, so and specifically it can be viewed as a voltage dependent capacitor, because the value of the capacitance is dependent on the reverse bias voltage that you are applying. Okay, so moving forward, okay, now we'll look at diode in forward bias. Okay, so when do we say that the diode is in forward bias? So when the n-type region is at a lower potential, when the n-type is at a lower potential than the p-type region, the diode is said to be in forward bias. Okay, so in this case the depletion region width is shortened. Why is it shortened? Because the external electric field is now in this direction. We know from equilibrium the built-in electric field is in this direction. Because these two are opposing, what happens is, in effect, the depletion region width actually decreases. Okay, so the depletion region width is, like I rightly mentioned here, is shortened. Okay, and the built-in electric field now decreases. Okay, so what happens now when the depletion region width decreases is the minority carriers in each region increase. So how is this possible? Because this is possible because of, so purely because of diffusion. Okay, so let me explain diffusion now in simple terms. Now that the depletion region width is decreased, there is a more possibility of holes in this p-type region to cross over the shortened depletion region and move over into the n-type region. Similarly, the same argument holds for the electrons on the n-type. So the sea of electrons here now can easily cross this shortened barrier and move into the n-type region. So the electron entering the p-type is nothing but this becomes the ink drop and this becomes the water. Similarly, the holes moving over from P to N, the hole that is moving is nothing but the ink drop, and the electrons over here is nothing but your water. Okay, so now diffuse, whenever there is a concentration gradient, immediately what has to come to your mind? Whenever I say concentration gradient, the thing that has to come to your mind is diffusion. Okay, so because of the external applied electric field or the voltage, it is resulting in shortening the depletion region width, and this shortening of depletion region width is facilitating diffusion currents, that is holes moving from p-type to n-type and electrons moving from n-type to p-type. Okay, right, so here at the interface, if you see, the electrons coming over from the n-type are more over here, but as they move away from the interface towards the contact, this is the contact, the concentration gradually decreases. The same thing happens here. As the holes cross over into electrons near the interface, these become minority carriers on the n-side. As they move away from the interface towards the contact, the number of holes decreases, of course. Okay, but near to the contacts, because it is still an n-type semiconductor, near to the contacts, the current conduction or the transport of charge carriers occurs through majority carriers, that is holes. And similarly in the p-type, near to the near to this contact, it is still a p-type region and the majority carriers are holes. Okay, so over here the current conduction or the transport of charge carriers takes place with the help of the majority carriers, that is holes, but near to the interface the transport takes place because of the minority carriers, that is electrons. Similarly on the inside, near to the interface the transport takes place because of the minority carriers, that is holes, but away from the interface or near to the contact the transport takes place because of electrons. Okay, so like I said, the immediate vicinity of depletion region, that is here, over here and here, the current consists mostly of minority carriers, like I said, because of diffusion, but towards the contacts it is primarily composed of the majority carriers. Over towards the contacts it is primarily the majority carriers, but near the interface it is mostly the minority carriers. Okay, right. Now this is how we summarize the PN junction. Okay, so you might have to remember this. Okay, so this is the diode current equation. Okay, this is also called the diode IV equation. So here id is the current that is passing through the diode, and vd is nothing but the voltage across the diode. Okay, and is is a reverse saturation current, yeah, like I mentioned here, reverse saturation current or a leakage current, which is very small. Okay, so you might start to wonder, I learnt about two currents. Okay, one about drift, that is mu, the other thing is about diffusion, that is d, but I'm not able to see those two in this equation, but the answer lies over in vt. So what is id? Id is nothing but is some reverse leakage current, e power vd by vt minus 1. So what is vt? Vt is nothing but the thermal voltage, which is nothing but kT by q. But what is kT by q from Einstein's relation we have seen previously? This is nothing but d by mu, isn't it? So in fact the voltage that I have put over here is in fact related to both drift and diffusion. So both these two phenomenon are inherently present in this equation. So you might initially have wondered, where have these two gone? I am looking at a diode current, and previously this fellow has spoken about drift and diffusion, but now it should be clear that this equation in fact contains both drift and diffusion parameters. Okay, so this is a nice summary. The x-axis is your voltage drop across the diode, and the y-axis is the current that is passing through the diode. Okay, so when vd, the voltage drop across the diode, is negative, it is reverse biased, isn't it? When it is reverse biased, what we have seen, the depletion region width is very wide and the current is very low. The current is given actually by is. Okay, when it is forward biased, what happens when it is forward biased? If you look at the equation, this equation, if it is forward biased, when vd is positive, okay, e power some positive value is very high, so I can, it is very high compared to 1, so I can easily approximate this region with is e power vd by vt. Okay, again, so when vd is negative, okay, when vd is negative, this becomes e power negative value, this becomes very negligible, and a negligible value minus 1 is minus 1. So id equals to minus is in the reverse bias region, that is when vd is negative, and id can be approximated with is e power vd by vt when vd is greater than 0. See, this beautiful equation accommodates both the conditions, both for reverse bias and forward bias. So if you plug in appropriate values, you are able to see that id is equal to minus is in reverse bias, and similarly id is is times e power vd by vt in the forward bias. Okay, so uh, in effect I'll be drawing some important conclusions. So only when vd is greater than 0, or when it is forward bias current flows. What this forward bias also means, that P is at a higher potential compared to N. Okay, so current in a PN junction diode flows only from P to N. Okay, let me put it this way. So if this is my diode, okay, so this is my P region and N region. So current flows only in the forward bias. Okay, when it is forward bias, P is at a higher potential than N, so current flows only from P to N. Very good. But what is happening to reverse bias? So in a reverse bias, practically it is a very low value, but theoretically we almost equate the reverse saturation current, or IS, or leakage current, to zero. So one important conclusion here is, in a diode, okay, current only flows from P region to N region, and other direction, that is N to P, is strictly not possible. Okay, so that finishes this lecture. If you have any doubts, please write to my email or ping me on Telegram.